Okay, this is David Zierler, director of the Caltech Heritage Project. It's Monday, May 11th, 2023. It is great to be back with Professor Paul Asimow. Paul, great to be with you again. Thank you so much.
You're welcome. Thank you for coming.
All right, we're going to pick up. I want to clarify one point in this amazing story you shared with me where you found this fatal flaw in this paper by these eminent scientists. We didn't really get into how you characterized or how you thought about this disagreement. Clearly, the data told you what the data told you. But from their perspective, would you have considered this scientific debunking? Was this sloppy science on the part of senior people in the field, which is a phenomenon that can happen? Or was there some legitimate scientific disagreement that might add an additional dimension to the fact that you were assured that there would be a retraction, but there never was? So among those options, or maybe you'd like to choose another, how do you think about what it was that you corrected?
Okay, so just to be clear, last time I told two stories about meeting senior scientists that when I was a graduate student, I had found that there were issues with their work.
Right.
So the discovery that Dean Presnell's hypothesis for the origin of mid-ocean ridge basalts was thermodynamically weak is more important in the scheme of things, and we'll get to that. I think you're asking about this experience with reading a paper by Claude Arleg, the French geochemist, noticing there was something funny about it and working it out, and then having a chance, thanks to Al Hoffman, to go and explain it to Claude. It's an interesting problem. They used a statistical method of treating their data that can give a lot of insight, but in this case it ended up concealing the real underlying structure of the data and producing a bogus result. The method is principal components analysis. When you have multidimensional data that you can't visualize, because to do so truly you'd have to see it in many more dimensions than we can see in, principal components analysis basically says what are the most important combinations of the dimensions along which the data has lots of variance, and let's just reduce the complexity of the data by projecting it into that reduced dimensionality space, and then you can visualize it. It can be very effective. In this case, what they were doing was taking concentrations of many trace elements, and the periodic table is big, so there's lots of trace elements, and if you treat them all as independent dimensions, you can't really visualize everything. So let's try to reduce the dimensionality to the point where we can isolate the variability among different kinds of basalts. The additional wrinkle they put in, and this is the mistake they made, is in many cases in geochemistry, the concentrations of trace elements are less informative than the ratios between trace elements, because there are lots of processes that are not interesting to us that will change the concentrations, but they won't change the ratios. Right? So for example, if two elements very strongly partition into liquids during melting, if you have some source in the mantle and you melt it by a very small extent, those elements will have a very high concentration in the liquid. If you melt it to a larger extent, their concentrations will go down by dilution. But maybe we don't care about the extent of melting, we just care about the properties of the source. And so the concentrations are not informative because they also depend on the extent of melting. But if they're both very incompatible, they both strongly prefer the liquid, then the ratio of those elements in the liquid just gets mapped straight from the source into the liquid. And it's independent, almost independent of extent of melting. So it's better to look at the ratio because it tells you what you want. The problem with this paper is they chose to form ratios of all these elements by dividing them all by thorium, which is at very, very low concentrations in mid-ocean ridge basalts. The result that they got was they got very large ratios of all of these elements to thorium in mid-ocean ridge basalt, which made the mid-ocean ridge basalts look highly variable in their principal component space. Their principal component basically became dominated by pointing towards no thorium, towards division by zero. which is a very long vector because it goes to infinity, right? And so when they took data, which were relatively smooth, but near the origin in thorium concentration, and then basalt data for all these other islands, which everybody thought were more variable than mid-ocean ridges, which have lots of variability but at higher thorium concentrations. And when you only look at it as ratios to thorium, it makes these very actually scattered data look very smooth because you're dividing by a big number, and these very smooth data look very far from the origin because you're dividing by 0. And then they only looked at it in that projection space, and they came up with a conclusion that was clearly insane, but is what came out of their data treatment method. So the lesson that I took from this is if it's not there in the original data, and you come up with some way of handling the data and revisualizing it and reprojecting it, and you get an insane result, maybe the problem is in your way of handling the data and not in the data itself. So that was that story. They didn't do anything wrong. They just processed their data in a way that might have created insight, but ended up creating obscurity.
Yeah. The broader picture.
Only by going back to the original data before they had munged it was I able to see what was going on.
The broader question about scientific disagreement, how this struck you as insane, as you called it. It was just totally off, right? Obviously, you can't get in their head, but how might it be defensible that they looked at this data and clearly it did not look insane to them? Is it just simply that they were wrong? That was the nature of my question. Or is there some deeper scientific disagreement where you can see legitimacy on their side and there's an agreement to disagree? Or no, they're just wrong. It's that easy.
It was just wrong. It was a conclusion that was not supported by the data, that was that emerged from handling the data in a way that was inconsistent with the actual nature of the data and the uncertainties in the data. And there is actually there is a mathematical error underlying what they did, which is that principal components analysis is a vector algebra operation, and concentrations of trace elements act like vectors, but ratios do not. They do not have the mathematical properties of vectors. And so, actually, yes, what they did was formally incorrect.
Yeah.
So.
And the breakdown is laziness? It's in the review process?
Oh, it's in not everybody understanding the mathematics at a deep level, both the people that were doing the work and presumably the reviewers, so that, yes, this made it to press even though it should not have. This is my experience, not that unusual. The peer review process is ineffective, or at least incompletely effective at catching things that look good but are not.
And nothing smacked of fudging or fraud on your part.
No, it was an honest attempt that didn't work out well. But this is hopefully one of the things that we scientists all appreciate, and that we teach our graduate students to appreciate. Just because something is published, peer-reviewed and published, does not mean it is right. And the literature is full of junk, and it takes discretion, and it takes time, and it takes testing and replication, of course, to figure out how much of the literature is junk. And undergraduates generally don't appreciate this, and the general public doesn't appreciate this. It seems sort of like the secret knowledge that at some point during your scientific career, hopefully in graduate school, you come to appreciate that science is imperfect, and it is our role to work towards perfecting it, a goal we will never achieve, but you can't just take something as given because somebody published it.
In your experience, how rare of an event is it where a graduate student discovers something so wrong by scientists so eminent and the reputational value that that confers. Have you witnessed this before? Have you heard stories from others, or is this truly unique as far as you can tell?
Oh, it's not unique. No, it's I have no way to quantify how common it is, but
it does happen.
It happens, and it's one of the ways that you recognize that somebody is going to grow up to be influential.
Yeah.
Right. Is that at least once that they strike gold, just going about their business, investigating and testing things, they discover there is something that needs to be fixed. There is a new way of thinking of this problem, and when you think of this problem in a new way, you get to a different and better answer.
All right, so to broaden the discussion out about, this experience as it relates to the overall dissertation, if we were to imagine a puzzle, what piece would this be out of how many?
So that's not in my dissertation. That was just a throwaway. We read this
wow.
paper. I saw there was an error with it. I came back to the reading group and said what the fix was, and happened to then have the opportunity to present the fix to the original authors.
And it didn't change the trajectory of what you were focused on otherwise?
Right.
Wow.
It was ancillary geochemical learning.
Okay.
No. More fundamentally, the sort of main thread of what led to my thesis started in a more formal reading group where we read these papers that were trying to parameterize polybaric fractional basalt melting. We decided we should approach this problem thermodynamically. We brought in Mark Hirschman and the MELTS code. I started hacking at the code. Once I got it to the point where I could run the thermodynamic path that we thought was relevant, I very quickly discovered that it behaves differently from our intuition, where our intuition is coming from thinking about pressure and temperature as the independent variables the way people usually do. But during the mantle melting problem underneath mid-ocean ridges, pressure and temperature are not the independent variables. And we were not the first ones to say this. It actually goes back to the work of a petrologist at Berkeley in the 1950s named John Verhoeven. Verhoeven said this is a constant entropy process, and gained considerable insight from that. But the modeling tools that were available to Verhoeven in the 50s didn't let him work out all the implications of this idea.
These were computational limitations?
Data limitations as well as computational limitations. The idea of taking this sort of thermodynamic framework for thinking about igneous processes that Verhoeven pointed the way towards was picked up by his colleague and co-author at Berkeley about 20 years later, Ian Carmichael, who had this remarkable insight and then spate of productivity where he said, we can do igneous petrology from a thermodynamic modeling perspective if we had these kinds of basic data. So let's go and get them. And he said, well, we need heat capacities of components in silicate liquid. And he got a student, Jonathan Stebbins, who within a few years was doing that better than anybody else. And we need densities of components in silicate liquids. And he got a student, Rebecca Lang, who within years was doing that better than anybody else. And we need compressibilities from ultrasonic velocities in silicate liquids. And he got a student, Mark Rivers, who within a few years was doing that better than anyone else. And we need a model into which to assimilate all of this data and make predictions. And he got a student, Mark Giorso, who within a few years was doing that better than anybody else. And it was just this burst of this Carmichael group of putting together all the pieces of quality data and understanding that by the 1980s and the 1990s led to this thermodynamic model that I'm still using, that Mark Giorso has rightfully gotten most of the credit for, but it's rooted in his PhD thesis with Carmichael and the modeling framework that they developed. So Verhoeven was, I credit with the insight that you should think of mantle melting as an isentropic process.
As opposed to what?
Isothermal or isenthalpic. There was actually an argument in the 70s over whether enthalpy or entropy are the right quantity in which to do this problem. And most people came down on the side of entropy. there are still some who argue for enthalpy. The point is, while entropy is a really useful quantity, it's also a very tricky one. It's not very intuitive, and we don't have an entropy dial we can set on an experimental apparatus to control the entropy during an experiment. We have a temperature dial we can set to control temperature during an experiment, but that's not how it works in nature. In nature, when you have no heat flow and the process is reversible, the second law of thermodynamics tells us that the entropy is constant. And in that situation, where you're not in equilibrium with an external heat bath that regulates the temperature will do whatever it wants. And if it wants to heat up, it will heat up, and if it wants to cool down, it will cool down. And if you impose a temperature, you are deciding how the system is going to behave, and you're controlling it artificially. But all our laboratory experiments are at controlled temperature. So you develop this somewhat difficult discontinuity where you can't really do the right experiment in the laboratory to simulate the natural process. Instead, you have to use the experiments in the laboratory to calibrate the thermodynamic model, and then you can use the thermodynamic model to describe the natural process. So petrologists doing experiments, looking at the way rocks melt and drawing their results in pressure-temperature space, and then drawing a reasonable path through pressure-temperature space that the rocks might follow, come up with one way of predicting how and where the rocks are going to melt. And once we had in hand a thermodynamic model where we could instead follow a path through pressure-entropy space and let the temperature be controlled by the internal thermodynamics of the system, we found that it was different, and in a couple of very basic ways. And our initial reaction, because we'd read these papers that derived an understanding of what should happen from pressure-temperature space, our first reaction to the results of the model was, this can't be right. And that was Ed's reaction. So I ran the model again. It definitely did what I saw it do the first time. And then we had this really, as it turned out, critical session at Starbucks where, on the back of a napkin, Ed remembered what he had learned from Thomson about how pressure entropy diagrams look in simple systems, and we sketched it out, and we saw that a simple system would behave just the way I was seeing the complex model behave. And so we wrote a paper where we said, look, this is how it behaves in a one-component system in pressure-entropy space. You can draw the complete phase diagram, you can analyze it rigorously, you can understand everything that happens, and clearly when you get to a solid-solid phase transition that consumes entropy, the entropy is no longer available to create melt, and you will freeze the system, not melt the system. And then we were able to do it in a two-component system, which is one extra dimension on the diagram, so they're a little bit more complicated, but you can still work it out in complete detail and show everything that happens, and the behavior is there on the two-component system. And then we see the same behavior in this complicated numerical model of a 10-component system, but now we believe it because we understand it in the simple system by analogy, and we can explain it, and it's a thermodynamically correct argument. And that was a very good paper, because everybody who took the time to read it saw the problem in a completely new way, and had their eyes opened and understood that this is the right way to think about the problem, and it leads to a different conclusion than the intuitive way to think about the problem once you recalibrate your intuition. So, that was the essence of kind of everything that developed into my thesis over 5 chapters of, if we model this process thermodynamically with both the complex model that is calibrated to try to do the full problem, but also looking back to simple systems whenever possible to see if the key behaviors are there where we can really understand them and explain them completely, then we can gain some insight. So my thesis, I don't remember exactly how many chapters, but the first chapter was this kind of first look at what happens when you are conserving entropy and melting and you hit a reaction in the solid phase assemblages, and the fact that it's the opposite of what people had thought. The second chapter was originally a talk that I prepared Ed to give at the Royal Society of London that analyzed the question of when you're decompressing a parcel of mantle underneath a volcano and it's following a constant entropy path and it starts melting, how quickly will it melt? And how much melt will it produce over a given decompression interval? And this is another thing that everybody thought they knew, but they had been trying to implement this sort of thermodynamic approach, but in very approximate ways that led everybody to consider that the rate of melting should be constant in some models, or that the rate of melting should be very fast initially and then slow down in some other models. And they're both wrong. It should be very slow initially and speed up. And we spent a whole paper explaining all the reasons why.
So this upended theory.
Yes. There were no experiments because it's not a process you can simulate experimentally. So there was a theory, there were simplified versions of the theory, there were attempts at a more complicated version of the theory that treated the experimental data wrong or, again, made mathematical errors. And this is when I first encountered another very senior scientist who did a lot of important work that I kept butting heads against. His name is Dan McKenzie. He's a professor at Cambridge for his whole career. He did a lot of the really important early work in the theory of plate tectonics as a geophysicist. And then he started moving into geochemistry, which can be a dangerous thing for geophysicists to do. And he wrote a series of very influential papers in the 1980s where first he worked out the first version of the theory of extraction of melt from partial molten rocks. Dave Stevenson also looked at that problem. They had slightly differing approaches in the 80s. And that was that first experimental project that I was working on in graduate school, was kind of following up on Mackenzie's way of thinking about that problem and doing the experiments to calibrate the parameters. But then Mackenzie also developed a theory for adiabatic or isentropic decompression melting. He wrote his equation for deriving the melting rate in a way that in this paper we published in 1997 we realized was mathematically incorrect. The multivariable calculus was attractive but wrong. Basically, if you have a function of many variables, you can write the total derivative, the rate of change of that function, as a sum over the partial derivatives of that function with respect to all of its independent variables and the derivatives of those independent variables. And that is true, but the variables have to be independent. And Mackenzie wrote the change in the entropy as a function of changes in pressure, temperature, and melt fraction. The problem is that the melt fraction is a function of pressure and temperature. And so that statement was wrong, and wrong in a fairly subtle way, and it took me until 2018 to explain this to Mackenzie, like get him to sit down and listen and understand what we were saying about his math.
But you got him there eventually.
I did, yeah.
Wow.
But also, because he's a good mathematician and a good physicist, but not necessarily a good geochemist, the way he parameterized the data seemed to fit the data, but it missed an essential property of the data. So if you plot from the beginning of melting, what we call the solidus, at the minimum temperature at any pressure where melt first appears, up to the end of melting, the liquidus, where the last solid disappears. Okay. Many materials, the solidus and the liquidus are the same, right? If I heat up water, ice. If I heat up ice at 0 degrees C, it will melt, and it will melt completely to liquid at 0 degrees C. Rocks don't do that because they're multi-component, multi-phase systems. They have a range of melting points at any given pressure between the solidus and the liquidus. So if you make a graph of experimental data ranging from all solid at the temperature where melting begins to all liquid at the temperature where melting ends, there's some continuous curve that connects them, going from 0, 0 to 1, 1. And Mackenzie looked at the available experimental data, which were mostly at pretty high melt fraction. There weren't any experiments in the 80s that got all the way down close to 0, 0. And he said, well, this kind of looks like a cubic curve. It's concave down and then it's concave up, so I'll fit a cubic curve to it. And then he went and used that cubic curve. And the property of that cubic curve is it was very steep near the origin. The actual behavior is that at about 0.2, 0.2 on this plot that goes from 0, 0 to 1, 1, there is a kink in the curve. It is not smooth and differentiable. It rises to a kink, concave up, and then another segment concave up, and together, if you smooth through them, they look concave down, but only if you don't have the kink. So if you fit a cubic polynomial, which is smooth, you get one functional form that goes through the data within error. But if you know that there's supposed to be a kink there and you fit it with this other functional form, you would get a very different behavior right down near the origin where there wasn't any data. And the fact that there should be a kink comes from insight that petrologists have about the way melting works, that a geophysicist coming to the problem and just looking at the data and drawing curves through it wouldn't necessarily have. So the sort of mathematical disagreement about the right way to write down this calculus was one thing, but more than that, the thermodynamic model that we ran predicted a different behavior for this function of melting rate near the solidus. And we spent a lot of time convincing ourselves that actually this was right and this is the way it should behave. And the experiments have been very stubborn, even now, 40 years later or something, not 40, 30 years later. Experiments have been very stubborn about confirming this behavior that our thermodynamic model says should be there, partly because the first version of the thermodynamic model exaggerated this effect due to some errors in the model or incomplete data sets in the model. The model was revised after my thesis around 2002, and it made this behavior a little bit more moderate, but still the same general effect. That's still there. So there was the chapter on the solid-solid phase transition. There was the chapter on the analysis of the melting rate. There was the chapter on testing some other assumptions or properties of Mackenzie's models about the way that melts migrate. And then there was the chapter where I tried to put it all together and run a complete model of, if this is the mantle source composition and it upwells under mid-ocean ridges, this is how much melt it will make and what composition of melt it will make. And then if it gets to the crust and fractionates, this is how it will evolve and what rocks you will make and what you can predict when you go out and pick it up on the seafloor. Put that all together into one big model. So there's a version of it in my thesis in 1997, but the paper actually came out in 2001, because this is what postdocs are for generally, is actually cleaning up the things in your thesis and getting them ready for publication. So I did some of that to get it all ready. And that paper ended up being published as part 4 in a series, where Hirschman was the first author on the first 3 parts of kind of finishing this goal that we laid out when Hirschman came of what does the MELTS model and this thermodynamic approach have to say about mantle melting. Turned out to be a lot more than one paper worth. So this chapter 4 or whatever of my thesis ended up being one of that series of papers. So the body of work as a whole was very original because it was the first application of this thermodynamic model that Mark Ghiorso and his mineralogy colleague Richard Sack built to do lots of things in igneous petrology. Lots of things even that they didn't imagine that it could do, such that their interface for running the model didn't have all the capabilities we needed, which is why I needed the code so I could get in and make the model do what I wanted it to do. It was really the first attempt to apply this model to this problem that is, in some sense, the most important problem in understanding igneous rocks on Earth, because the whole seafloor is covered with mid-ocean ridge basalt, and that's 70% of the Earth, and the Earth is always making this stuff and then recycling it back into the mantle and making more. It was the first attempt to take this thermodynamic model and solve this problem, and it has on it the fingerprints of lots of important prior work that led up to this synthesis of what you could do with this model. So it's rooted in intellectual parentage, I would say, goes back to Josiah Willard Gibbs and chemical thermodynamics, and to Norman Bowen and experimental petrology, and to Jan Verhoeven and this insight that this is an isentropic problem, and to Ian Carmichael and his mission to get the experimental data that you would need to actually implement this thermodynamic approach, and to Dan McKenzie, who did a lot of the physical theory of what is going on with two-phase systems and migrating melts, as well as the first attempt to really put together a quantitative model of how the mantle would melt and what compositions would come out. And Charlie Langmuir, who, we'll get to this, was one of my postdoc advisors, who in the 1980s with his student Emily Klein compiled all of the chemical data from the mid-ocean ridge basalt glasses and processed it in such a way that you could see through the noise and the secondary processes and develop a theory about what controls the variation among all the different segments of the mid-ocean ridge, which ultimately is what I was then able to test with my model, is can I reproduce the correlations that Langmuir observed. And Mark Giorso and Richard Sack, and they're assembling this actual working model that took all this thermodynamic data and allowed you to make computational predictions in a reasonable time scale. And Thompson and his way of thinking about phase diagrams, especially phase diagrams with non-traditional independent variables like entropy, and Ed and his awareness of all these things that were out there in the literature to point to me so that I could put them together. And Mark Hirschman, who's only a few years my senior, but was very influential in helping me learn what this model could do and how to use it, and collaborating on this whole project. So I had in my thesis presentation a slide that was titled something like "The Giants on Whose Shoulders I Am Standing," that had a pyramid of cartoonish, shirtless giants holding a big club with really big ones at the bottom, and then some standing on their shoulders and some standing on their shoulders and me standing on the top. But these are the scientists to whom I give credit for laying the intellectual foundation for me to put together this synthesis that I spat out into the world in my thesis.
Besides Ed Stolper having the insight to put together all of these disparate pieces and focus your attention on it, how related was that to what he was doing, his own research at the time?
Ed has very much worked for his career in a mode of bringing in excellent students or staff members and guiding them to master some area of science and produce interesting results. And so his work for so long, I mean, since he was an assistant professor, has been so tied up with mentoring students and postdocs to do interesting things that it's actually hard for me to say what Ed is working on at any given time, rather than what Ed's group is working on. Not to take anything away from Ed, right? He has a mastery of all of these areas of petrology and meteoritics and geology.
You're speaking to his devotion as a mentor.
That too, right? But when you ask, how does this relate to Ed's work, it's actually hard for me to answer, because Ed's work is meteoritics in collaboration with his staff member John Beckett, and it's experimental metrology in collaboration with his staff member Mike Baker, and it's infrared spectroscopy in the behavior of water and CO2 in igneous rocks and melts in collaboration with a series of students and his longtime staff member Sally Newman, and it's thermodynamic calculations in collaboration with his postdoc Hirschman and his student me. And he doesn't write that many first author papers, right? Quite few. Because he works really well at identifying talent and mentoring talent and creating things in collaboration with junior scientists. So
those are skills that make for a great administrator as well.
Yes, right. And you can only do so much yourself. this is why our model of doing science in academic institutions is pretty successful. It is a force multiplier that allows someone with ideas and the ability to inspire others to follow up on those ideas can end up producing a lot of science that they would not be able to produce working in isolation. So yes, I have great admiration for Ed and his knowledge of many areas of science, and especially for his ability to inspire and mentor young scientists, which is why there are so many students and postdocs of Stolper out there in running their own research groups now and carrying on his influence.
Who else was on your committee?
Dave Stevenson, who was there from the beginning because I started working on this experiment. Peter Wiley, whose name has not come up yet, but Peter was is an experimental petrologist who did a lot of important early work on melting of volatile rich rocks, CO2-bearing rocks and water-bearing rocks. He himself had one of these moments where early in his career he proved that something that Norman Bowen, kind of the father of igneous petrology, something Bowen had said was wrong. So he burst onto the scene in a big way with one of these disproofs of a dogma back in the early 1960s. So Peter came here. He was hired from the outside to be chairman in this division. We've only done that once.
Yeah.
Every other chairman has been hired from the inside, but after the Wasserberg chairmanship fell apart in disarray, they brought somebody in. So Peter Wiley came from Penn State, bringing his experimental apparatus with him and setting up a lab up on the 3rd floor. When I arrived on the faculty in 1999, Peter handed me the keys to the lab and said, "I don't have anything to do with it anymore." So Peter was on my committee. He was a very big fan of our work and our kind of new ways of looking at these problems. And I learned a lot of phase diagrams and experimental methods from Peter, but he wasn't really at the heart of what we were doing in terms of bringing this thermodynamic reasoning. That wasn't Peter's specialty. But I was just, yesterday, a graduate student had just turned in their thesis and was saying, "Oh, I turned in my thesis." And so this had me remembering when I turned in my thesis. In those days, you got it printed and bound, and you handed a hunk of paper to the members of your committee 2 weeks before your exam. Of course, that's not how it works anymore. Now you get a PDF, right? But I got my thesis printed and bound, and looking for my thesis as opposed to all these other theses. Should have a copy of it somewhere on my shelf, you would think. Anyway, you can see a range on my shelf of what PhD theses look like. So I handed it to Peter, and he said, "Oh, it's a nice thin one." And then he opened it up, and he said, "Oh, it's double-sided." So Peter retired in about 99, about when I started and took over his lab. He's still alive. He's still Professor Emeritus. He's not been coming in very much lately, I think. His mind has been slipping of late. But in his retirement, he had ambitions to write books and keep learning and try to appreciate the sort of new ways of thinking about these problems. He came and he sat through my freshman class just to see how I was teaching it.
And very little or no interaction with Tom Ahrens as a graduate student.
That's right. Not on my committee, not involved in the work that I was doing. He was in geophysics and planetary science, and this is a geology thesis with kind of geochemical implications. So I'm actually trying to remember who else was on my committee. There should have been a fourth member, right?
Anything interesting
So
from the oral defense that might spark that memory? Any curveballs?
No. Defenses are misnamed these days.
Yeah.
Right? At least here, we are not a very adversarial community. And if the advisor has done their job and prepared their student
It's a
for their
discussion.
defense, it is a discussion, because the student should be the expert on the subject, not just amongst the committee, but in the world. And I find this is generally true, that the thesis defense is essentially a presentation, and not so much a defense, unless something has gone quite wrong. The other member of the committee was Mike Gurness,
Oh, wow, okay.
with whom I still collaborate.
He must have just arrived at that point.
I think he'd been here a few years. I don't know exactly when he came from Michigan. That's interesting. So
Was that for the computational angle to have Mike on the committee?
Yes. Yeah, I think that made sense. Okay, and the chair of my committee, who was your academic advisor, was Jeff Blake.
Oh.
Who also was kind of randomly assigned my academic advisor when I was thought of as a geochemistry student, and somehow remained my academic advisor when I decided to be a geology student, even though he's not in the geology option.
And is that SOP for that not to have been Ed?
Yes, absolutely. This is key. In our division, every student has an academic advisor who is not the thesis advisor. And the committee chair is the academic advisor.
This is to prevent blind spots, essentially?
Yeah. Until you get to the point of thesis defense, it's so that there's somebody else paying attention who can manage conflict that arises between a student and a thesis advisor.
Mm-hmm.
And then at the thesis defense, it is to avoid the person chairing the committee being too close to the work.
Mm-hmm. Mm-hmm.
Actually my committee was Blake, Stolper, Wiley, Gurness. Interesting. I did not collaborate with Gurness during graduate school, but years later, after I joined the faculty, we advised a student on a joint project trying to combine thermodynamics and geodynamics, a student named Laura Hebert, and we are currently jointly advising a postdoc, again trying to do the same idea of combining thermodynamic calculation and geodynamic calculation. So the geodynamics tells you how things move around, and the thermodynamics tells you what happens as they move around, and hopefully you can run a model that is not so computationally intensive that it doesn't go anywhere.
At any point in your graduate career, in the later years especially, was there any noise about you returning as a faculty member? Did anybody intimate anything to that effect?
No. Not that I can recall.
So that would not have influenced where you wanted to go for your postdoc, having an idea that you'd come back.
Right. No, I think they held their cards pretty close to their chests until they were able to get an offer through. And it must have been a difficult process, because there wasn't really a search going on as such, and we don't like to hire our own students. It's frowned upon. And I never applied or gave a job talk other than my thesis defense. The faculty must have just sat down and said, this is one of the most exceptional students we've seen, we need him back, and yeah, he does work that's similar to what Ed does, but he'll do something different, and let's just bring him in. What we would call a target of opportunity hire. Mm-hmm. When you see somebody extraordinary, the culture at Caltech is forget your strategic plan, forget whether the provost said you have a search open, just get this person. Every now and then we do that.
So there was no open line for you. They really made one.
Yeah.
Wow.
At the same time, my hire made sense in the context of what was going on during Stolper's chairmanship, which was a complete overturn of the geochemistry faculty.
Yeah.
Right? So Bob Sharp hired a geochemistry faculty in the 1950s. By the 1990s, they all retired, and it was time for a big burst of new hiring. And I ended up being part of that burst. So we try not to draw like a direct line, like this person retired, we need somebody in their field, right? But, you know, Sam Epstein and Hugh Taylor and Jerry Wasserberg and Lee Silver and Peter Wiley all retired, and John Eiler and I and Jess Adkins and Diane Newman and a bunch of new geochemists were hired kind of in a cluster or a big burst. That was one of the repopulation things that Ed did while he was chairman. The other was create the geobiology option and set it off, which involved both young hires like Diane Newman and Victoria Orphan and eventually Jerry Ledbetter and Alex Sessions, but also something we do pretty rarely, which is a senior hire, which was John Grotzinger, across from MIT. So yes, when I was finishing up and looking at postdocs, no, I don't think I had an idea that a movement was afoot to get me back. So shall we move on to the postdoc search process?
Yeah, so what mentor advice did you get about best postdocs for you, if any?
I don't know if this was mentor advice or if I figured it out for myself, but there's kind of two different sorts of postdocs. There are soft money postdocs. Somebody writes a research grant. They include in their research grant salary for a postdoc, and then they go and try to find a postdoc to do the thing that they said they would do in the grant. And then there are fellowships, or hard money postdocs. There are institutions that have enough endowment sitting around that they can, every year, hire a postdoc, and they're hiring the person to do whatever that person does best, rather than matching a person to a project that has been funded. Hard money postdocs are better.
Particularly if you have ambitions to improve the thesis research.
If you know what you want to do. Well, because I mean, this is the problem with postdocs. Postdocs spend half their time publishing their thesis and half their time looking for a job.
Yeah. Yeah.
You would like them to do something else
new
in between.
Right.
Not all postdocs do. I don't necessarily love the idea of postdocs from the point of view of being a faculty member and mentoring them. They're a little hard to manage. But from the point of view of being a postdoc, yes, it's nice to have time to finish up this unfinished work from graduate school. It is nice to have the intellectual freedom to define what you think is important to work on next. So
that's only applicable in the hard money variant.
Exactly. So long as the institution provides you the resources that you need, experimental, computational, whatever, to do the work, and that there are mentors there that are interested in what you're doing and qualified to contribute to it and help you continue to learn, right? You don't want to just go somewhere and get salary support to be completely alone and have to make up everything from scratch. That's not useful. The other thing about hard money postdocs is there's a calendar. They post an ad, you apply, they make an offer, there's a cycle, it's more reliable. Whereas soft money postdocs, you know, whenever someone happens to have money, they might go looking for somebody, and they're harder to find, and they're less reliable.
What about on the personal side? You're a family man at this point.
Right.
What are the considerations there?
Yes. So
is there a two-body problem?
No, because I got married in 1993 in my third year of graduate school. We had a son in 1996 in my fifth year of graduate school. My first wife, Jenny Factor, is a poet and had also trained as a Montessori teacher and was not really tied down to any particular place or job or time, and didn't especially want to come back to California after college. Did because I was here, and was happy to leave. So no, I didn't feel especially constrained by moving with Jenny and Lev at that time. Maybe I should have been, but so I applied for the Miller Fellowship at Berkeley, which is a 3-year hard money position. I was nominated for the Junior Fellowship in the Society of Fellows at Harvard, which is sort of a postdoc. It's not exactly comparable to other things.
Yeah. And the Miller Fellowship is associated with what school at Berkeley? I mean, that's bigger than geology.
Oh yeah. That's campus wide.
Yeah.
Big program. I applied for the Carnegie postdoc at what's now Carnegie Science, but was then the Geophysical Lab, or Department of Terrestrial Magnetism, or both.
And that's in DC.
That's in DC. And I applied for the Lamont Fellowship at Lamont Doherty Earth Observatory of Columbia. And I did not get an offer from Harvard for the Junior Fellowship, and I did not get a Miller Fellowship. I don't remember whether I got an offer from Carnegie. But given the directions that I wanted to go in, Lamont made the most sense. At that time, I was doing computations. I hadn't really gotten my hands on any real rocks to measure myself and work out what they meant and test my models against them. And I'd moved away from experiments a bit. And so with a fellowship at Lamont, I could work with Charlie Langmuir, who's an ocean-going petrologist. He goes out and he dredges rocks off the seafloor and he brings them home and analyzes them, and I wanted to learn to do that. And Dave Walker, who's an experimental petrologist and who had been influential a generation earlier in Ed's early career. And I wanted to learn experimental methods from Walker.
Had you known either of them, or just by reputation?
Just by reputation. And then also there was a young computational geodynamicist who had been a student of Mackenzie, Mark Spiegelman, at Lamont, and I wanted to continue, or at that point make a first attempt to do the kinds of things I later did with Gurnis, of integrating thermodynamic calculations with fluid dynamic calculations, and so I wanted to work with all three of them, and with the Lamont Fellowship I could do that. And that postdoc was a really good time, scientifically. I got my thesis papers out without it consuming all of my time. After 6 months that I'd been there, I got an offer to come back to Caltech. I said, great, hold that for 18 months. I'm going to finish my 2-year postdoc here, and Caltech is very patient about giving junior faculty higher time to finish their postdoc and get some work done before we drop teaching and committee work and all this stuff on them. So having my thesis out of the way, knowing what I was going to do next, then a postdoc is just 2 years to do your own work, and it's fantastic.
So what were the loose ends in the thesis? What did you feel like you needed to clean up?
There were 2 chapters that were not yet published that ended up being 3 papers that came out in like 99, 2000, and 2001 or something like that. So I graduated in 97, so it took a while to get those out the door. They needed polishing. Writing a paper with Ed can be a slow and iterative process. He reads very closely and very carefully and doesn't let anything pass, so you really have to cross every T and dot every I before you can publish a paper with Ed, and I admire that greatly. I don't think I'm nearly as careful. But then I started several new things. So I started doing multi-anvil experiments, which is why when I came here I built a multi-anvil device. Charlie handed me a data set of rocks that they had picked up at that point 7 or 8 years earlier on a cruise to the Mid-Atlantic Ridge, and because one student left and one postdoc left, the data had never really been organized and nothing had been written about it. So I started systematizing those data, which happened to be from the segment of the Mid-Atlantic Ridge near the Azores archipelago, which is a geochemical anomaly that contributes a lot of extra water to the source. And so that is why I started working on generalizing my approach to mantle melting, which had previously not considered the influence of water, to consider the influence of water, so that I could do something with these rocks from the Azores region. And that led to, first of all, a Nature paper that Langmuir and I wrote on just conceptually understanding the influence of mantle water on mid-ocean ridge melting. That brought together several new pieces that were sitting out there kind of waiting to be integrated. One was the thermodynamic modeling approach that I had developed and its generalization to account for the presence of water. The other was Langmuir's model of similar processes that could be tweaked to at least give comparable results to show that the two models agree. The other is George Rossman's work. So George Rossman, starting with his student Dave Bell, triggered a revolution in how we think about what water is doing in the Earth's mantle. Right? We know that there are hydrous minerals. They have, when you write out their formula, they have H2O molecules in them, or they have hydroxyl groups in them. And then there's lots of minerals that are nominally anhydrous. You write out their formula, there's no hydrogen in the formula. What George showed is all the anhydrous minerals have some water as a trace constituent. And he's spent much of his career trying to quantify how much water there is. But the way water behaves, if it's present in the mantle as a trace constituent in all the minerals, is fundamentally different from the way it behaves if it's a major constituent of a very minor hydrous mineral. Right? So if you have, let's say, 200 parts per million water, it's either kind of 200 parts per million in all the minerals, or it's 5% of a mineral, which is then really, really small fraction of the rock. And when it's 5% in a mineral that's a really small fraction of the rock, when you start melting it, that mineral melts and then it's gone. And now there's no more influence of water. Whereas if it's distributed through all the minerals, it slowly leaks out and it affects the whole melting process. So I came up with a way to describe that behavior, influenced by George's insight of what the water is actually doing there. That led to this Nature paper, which gives this very counterintuitive result that when you add water to the mantle melting system, it promotes melting, and so it increases the total amount of melt that you get. But extending this idea that I mentioned earlier, that the onset of melting is very slow and it speeds up as you go, it makes it even slower, and it makes for this very large volume that melts just a little bit. And so the average extent of melting, which controls the incorporation of trace elements into the oceanic crust, the average extent of melting goes down, even though the total amount of melting goes up, because you're melting a much larger volume of rock. And nobody had understood that, so that was the simple point that was worth saying in Nature. A Nature paper is a good calling card for a young scientist. I wish it weren't true that these couple of journals are so influential, but having that paper was a good thing.
The idea there is that, publishing in Nature transcends the specificity of your discipline.
Right. That
there's something more important to convey.
Yeah.
Which was what? Why did it make the cut for Nature?
Because it combined a couple of new ideas that were permeating the literature and showed what their implications were in ways that nobody had thought of yet. And it's still like, if people write a paper that has something to do with water and mid-ocean ridges, that's the paper they cite. Right? Like Asimow and Langmuir, just because it was simple and to the point and it explained what's going on.
Did you end up working more closely with Langmuir than Walker than you had originally anticipated?
Yeah. Walker and I didn't publish anything. I learned to do experiments in his lab. I played bridge in his office a lot. But we didn't actually finish anything. And that was fine.
Personality, just science? What was it?
What was most new and exciting and could be accomplished in a reasonable amount of time.
Yeah.
Yeah. So then, just as basically Charlie handed me this data set of mid-ocean ridge basalts that I used as an excuse to figure out how to deal with water in the mantle, he also handed me a data set on abyssal peridotites, which are the rocks that you find in a few places on the seafloor that are the residues that are left behind after the oceanic crust is pulled out. They're what we call depleted peridotites that are a complementary way to study the melting process. Start with fertile mantle that comes up under mid-ocean ridges. We partially melt it, we make basalt, and we leave some stuff behind. But the stuff that we leave behind, due to accidents of tectonics and major faults and fracture zones, occasionally gets exposed on the seafloor where you can pick it up. And a previous, and they provide a very different way of looking at the melting process that's sensitive to the details of melting in a different way that allows you to see things that you can't see from looking at the liquid. And we have a good sort of simple understanding of why that should be true and why we should look at the abyssal peridotites to try to learn about the melting process. And the previous holder of the postdoc position that I was holding, Yaoling Niu, had started working on these peridotites and compiled all the data and had left, leaving this unfinished compilation. And I started looking at it, and I realized he had done all sorts of dodgy things with it, and it needed to be redone and reprocessed. And I did that, and when I looked then at this data set compiled and sort of with the holes filled in my way that I thought was more supportable, I noticed something very interesting, which is, from a trace element perspective, these rocks look like residues of fractional melting, meaning as you're melting the rocks, the melt is being pulled out, and it's pulling out the trace elements with it and decreasing their concentration very quickly. And everybody was saying, and this was part of what Mackenzie was responding to with all of his work on melt migration, was that it's a fractional melting process in the mantle, and part of the evidence for that is the trace elements in the abyssal peridotites. But when you develop the ability to model the major elements, which is more difficult than modeling the trace elements, but this is one of the things my model could do, when you look at the compositions of the abyssal peridotites, they do not look like residues of fractional melting. In fact, they look like residues of batch melting, where the liquids are continuing to equilibrate with the solids throughout the melting process. So how can it be both? There was at that time no synthesis, no model that could explain all the evidence from these rocks. So I wrote a single author paper while I was a postdoc, published in Earth and Planetary Science Letters, which is a good journal, widely read, titled A Model That Reconciles Major and Trace Element Data from Abyssal Peridotites. And basically the trick is very simple. You do some fractional melting and you do some batch melting. And the trace elements are sensitive to the fractional part and the major elements are sensitive to the batch part. So Charlie just sort of said, here, Yaoling left this thing behind, see what you can do with it. And I saw what I could do with it, and I wrote this paper, and Charlie didn't feel the need to put his fingerprints on it, so it was my work. And that was another successful paper and a good outcome of the postdoc time. And the other thing that came out of that postdoc time is that Charlie came to appreciate my ability to systematize data sets. And so a few years later, when he wrote a proposal for a research cruise to go out and pick up a bunch of rocks, he invited me to participate, like at the PI level, even though I'd never been to sea before.
So your whole time at Lamont, you didn't go out to sea?
Right.
Huh.
No, I didn't end up going to sea until the fall of 2004, 5 years after I came back here.
Uh-huh.
And I had a lot of conversations with Mark Spiegelman, the fluid dynamicist, but we never actually got anything going really in terms of joint work.
This would be obviously a bit far afield for you, but I'm very interested in how, as an oceanographic institution, Lamont was really at the leading edge of plate tectonics, where Caltech really missed the boat on
Mm-hmm.
that one.
So to
Pun
speak.
kind of intended. Did you get that sense coming from GPS? Did you get that appreciation in some way about why a place like Lamont would have been a leader in the plate tectonic revolution?
Not that much. I mean, you pretty much said it, that the secrets of the world turn out to be revealed on the ocean floor.
Mhm.
And if you're not in the habit of exploring the ocean floor, you would miss it.
Mm-hmm.
And that just wasn't the kind of work that Caltech was doing.
Yeah.
But that was still the kind of work that Lamont was doing, so they were learning a lot of things. But a lot of the fundamental information that is out there on the seafloor had already been mined and systematized. No, my experience with my postdoc was that compared to the Division of Geological and Planetary Sciences here, which is now about 40 faculty, and when I was a graduate school student, it was probably closer to 30. And 80 some graduate students, and I don't know, in those days 50 some, and maybe now 100 some postdocs, and just a handful of undergrads. This is a size of community that, at least when I was in graduate school, I was able to pay attention to the whole thing and go to the planetary seminars and go to the geology seminars and go to the geophysics seminars and have a sense of all of earth science, at least all the earth science that was being done at Caltech. And then I went as a postdoc to Lamont, where there are hundreds and hundreds and hundreds of earth scientists, and it's too much. So I rarely left the geochemistry building, except for a few excursions to the geophysics building to talk to Spiegelman. I didn't go to the oceanography building, and I didn't go to the atmospheric science building, and I didn't go to seminars in those areas of science. So my focus ended up really narrowing due to the size of the institution, and in some sense, to me, the unwieldiness of it.
There's an irony there. The bigger the place, the more narrow your focus.
Yeah. So it was a good time, and I really value the 2 years that I spent there, and I learned a lot, and I wrote a couple of papers that turned out to be really useful for my career. But I was not, well, they didn't make me an offer. Well, there's sort of an offer to stay. After your postdoc there's something called the Stork Doherty Lectureship that you could move into, but I wasn't that interested. The other thing that happened while I was there is just about the time that Caltech sent me an offer, Harvard was searching in petrology, because as they do, they'd repeatedly denied tenure to all the junior faculty in this area. And I had been an undergrad there, and I knew the people there, and Rick O'Connell, who of course was a Caltech alum and had been the second reader on my bachelor's thesis, called me up and said, "Will you apply?" And I said, "No, I have no interest in being a junior faculty member at Harvard. It's not a supportive and friendly place to go. I know that Caltech is a supportive and friendly place to go, and I would rather go there." So I declined the opportunity to actually apply for a job, just because it didn't seem like it would be any fun.
Did you spend time on Columbia's campus at all?
Almost none, right?
So it really is that removed.
Yeah. So the undergrads mostly live down in Morningside Heights. The graduate students typically go back and forth. Many of them live downtown, take their classes downtown, commute out to Lamont to do research. The postdocs, and especially the research staff that are not also professors in the Department of Earth and Environmental Science, they live at Lamont, and they have no particular reason to go to the city except to see a show. Some of them choose to live in the city just because that's the lifestyle they want. I was more interested in a sort of suburban existence at that point with a young kid, and wanted parkland nearby. So we lived in Palisades, and rarely went to the city, and almost never for work, just because, hey, it's New York City. Until the last 6 months that I was there, so this is now spring of '99, when Jenny and I separated, and our approach to that was we rented an apartment in Manhattan, not far from Columbia, And Lev, our little toddler, lived in Palisades in the house, and Jenny and I went back and forth.
Huh.
Rather than
Creative
each
solution.
of us having our place and the kid going back and forth.
Uh-huh.
So the last 6 months, half time I was living in an apartment near Columbia. But even so, I was then getting in the car and driving out to Palisades every day for work. I wasn't going to Columbia campus that much. Yeah. If you're newly single, New York City is not a bad place to be.
Sure. So you said it was 6 months when Caltech reached out.
Mm-hmm.
So 6 months seems like they were really holding back. You know, they would have made the offer sooner, but it's almost like they needed to give you a little breathing room before they did.
Or that's just how long it takes to get an idea, shop it around the faculty, get letters, get a package written, get it voted on by the faculty, get it voted on by the IACC, get it voted on by the trustees.
And so this was just an offer. This was not an offer to apply.
Right.
And as you said, no job talk, nothing like that.
Exactly. So when, you know, my students and postdocs ask me for advice about how to apply for jobs,
get an offer.
I don't necessarily have all
and
that much.
Is your sense, was Ed driving that, or is it really a collective effort?
I think Ed, being chairman at the time and having been my advisor, must have done his best to drive from the back seat. Like, I'm sure he wanted this to happen, but if he let it, it would seem inappropriate. So I don't know exactly how he pulled it off or who was pushing for it or how it worked. That appropriately, these things have been and remained hidden from me. So obviously he was supportive and wanted it to happen, but I suspect he made it happen by influencing others to bring it forward.
I wonder also, you know, if there was any concern of how closely aligned your research was with Ed, where Ed's career was going, ultimately, that he would become less involved in the research. And
well, yeah, there was that, right? He was chairman, and I don't think it was clear at that point that he was then going to be provost or acting president or anything. But we've while our fields are clearly related, and it's been lovely to have each other to talk to all these years, we have not collaborated that much. Mm-hmm. We've done different things. So once I knew I was coming back, I started talking to Tom Ahrens, actually. Once Tom knew I was coming back, he saw this long-term plan to get his lab to outlive him by inviting me to take it over. You know, I built my own experimental lab and thought I would collaborate with Peter, but he really was done. And the work that I was doing with rocks that I had picked up while at Columbia, that didn't have anything to do with Ed. And so, yeah, it was some years before we actually collaborated on anything. And then so it worked out fine. Like, yes, we're both here, but I am not, and I don't think anyone would say I've been redundant.
Looking back, what was the value in holding off, in following through with your postdoc, not taking the Caltech offer immediately?
Several. One was finishing the things that I started as a postdoc and getting them published, and having the time to really dig in and do a good job on that stuff. One was time to actually write some proposals so that when I arrived here, I wasn't just starting fresh with my startup money. I actually already had some proposals in the pipeline for collaborative work with Tom Ahrens and for things that I would do with the equipment that I was building with my startup money. Yeah, it's just, you know, time to mature and get some work done and soak up a different set of colleagues and collaborators and a different culture. It's not good for someone to spend their whole career in one place, mm-hmm. and I'm pretty close to that. Mm-hmm. But no, I really appreciated having that time to work and breathe and do research and grow and just be somewhere else.
So last question for today, and it flows from the previous question. How did that extended time at Lamont inform the kind of professor you wanted to be in your return to Caltech? The lab that you wanted to build, the experiments you wanted to pursue, your persona in the field, all of the above.
So yeah, the equipment that I added to Peter Wiley's lab is the design of multi-anvil device that Dave Walker invented and that Dave Walker's former machinist who went into business built for me. So certainly what I brought with me in terms of experimental technique, I specifically learned there at Columbia from Dave Walker. The really systematic process of curating a collection of rocks and getting the most information out of it, and the idea of trying to measure everything you can measure on the same sample so that your data are multidimensional and rich. I learned that from Charlie Langmuir. What was practical and what was not practical in merging thermodynamic and geodynamic calculation. I made a lot of progress in understanding that through conversations with Mark Spiegelman, although we didn't actually do it. I ended up doing it here some years later with Gurnis, but I think those conversations were important in setting the groundwork for that. At the time I was there, Langmuir was very busy founding a journal, which I'm actually now one of the editors of, Geology, or Geochemistry, Geophysics, Geosystems, we just call it G-cubed. Getting divorced, having lots of projects going on, and he was not all that accessible to his students and postdocs. It was hard to get a meeting with him. You could turn in a manuscript to him and it would sit for a long time. And I definitely saw that as a counterexample of how I wanted to be a group leader and mentor. 25 years later, I find myself with a lot of the same behaviors and pathologies of being overcommitted and having too much going on and not actually being able to turn around a manuscript when somebody gives it to me. But certainly I had the ambition to be much more available and responsive and quick about things for at least as long as I could get away with it. And I guess I also, because I had the freedom as a postdoc to do everything, to do experiments and calculations and analyze real rocks and move all those things along, I learned that I liked working like that and I was going to keep doing it. And so I have, through my whole career, refused to pigeonhole myself as an experimentalist or a computationalist or a field geologist. I will do all of those things because they're all useful and they're all fun.
And you knew coming back to Caltech, GPS would be a perfect place to do that.
That too.
No surprise there.
Yeah.
We'll pick up next time when you return to Caltech.
Okay.
All right.